Hello. Today we're going to be talking about taking the derivative of an equation using implicit differentiation. The equation that we're going to be looking at is the square root of x squared plus y squared equals tangent of y. And so we want to find dy dx. That's what we want to find. So find dy dx of the following equation. We are going to use implicit differentiation. We're going to differentiate both with respect to x to both sides. This is going to require a chain rule here and a chain rule there. So to set this up, I want to take d dx of, I'm going to rewrite this in exponential notation, x squared y squared to the 1/2 equals d dx of tangent of y. So we're going to differentiate. The left-hand side requires a chain rule. The right-hand side also requires a chain rule. So let's start with the first side, the outside function being to the 1/2 power. I'm going to bring the 1/2 to the front and raise it to the negative 1/2. So bringing the 1/2 to the front, rewriting the stuff inside, and then to the negative 1/2 power, times x squared plus y squared prime. And I'm just going to use this prime notation to remind me later I need to take the derivative of this. To the right-hand side, the derivative of tangent is secant squared. And I'm going to rewrite the inside. And then the derivative of y. I'm not going to really do it right now. I'm just going to leave it in this prime notation to remind me in the next step that I need to take the derivative of that. Okay, so now this stuff is not going to change. I'm going to take the derivative of this. When I rewrite this, I'm going to move this down to the denominator. So to rewrite this portion of the left-hand side, this becomes 1 over 2 times x squared plus y squared to the 1/2. So what I'm doing here is I'm rewriting these two factors, and I'm writing this particular factor with a positive exponent. Now it's time to take the derivative of this part right here. The derivative of x squared is just 2x plus the derivative of y squared is in fact a chain rule. The derivative of the outside is 2, rewriting the inside, times the derivative of the inside, which I'm going to leave alone right now. I'm using the prime notation here to remind me later I need to still take the derivative of that. That is, write it in terms of dy dx. The right-hand side is still secant squared of y times, now I'm going to take the derivative of y. So that's going to be secant squared of y times dy dx. Okay, so looking at my equation, I have just one more prime to handle. I'm also going to I'm just going to take care of that prime right now. So I'm going to rewrite this first part. So that's 2 times x squared plus y squared to the 1/2, bracket 2x plus 2y dy dx, and bracket, equals secant squared of y dy dx. Okay, so one last thing I'm going to do is I'm going to distribute into this term. One thing that I should notice is that the 2's will cancel when I distribute it in. So this is going to give me x over x squared plus y squared to the 1/2. So that's the first distribution. Notice that there's no 2's because it would be a 2 over 2 and that is cancel out. Plus, and this I'm going to write in the following way. It's going to be y over x squared plus y squared to the 1/2 dy dx. So notice how I did not put the dy dx in the numerator. I'm just going to keep it off to the right because that identifies this whole term as being a dy dx term. Equals secant squared of y dy dx. Okay, so I have pretty much laid out what I need to do in order to solve for dy dx. So what I'm going to start now is the process of solving for dy dx here. So I'm going to rewrite this. So this is rewritten is going to be x over x squared plus y squared to the 1/2 plus y over x squared plus y squared to the 1/2 dy dx equals, and so then the right-hand side, that's going to be secant squared y dy dx. Okay, so I'm going to move this whole term to the right-hand side. I do that by subtraction. So I'm going to subtract y x squared plus y squared to the 1/2 times dy dx to both sides, y over x squared plus y squared to the 1/2 dy dx. And so this becomes, so the left-hand side is going to be just x over x squared plus y squared to the 1/2. The right-hand side is going to be secant squared y dy dx minus y over x squared plus y squared to the 1/2 dy dx. Okay, so now I have two terms on the right-hand side. They both have a dy dx in common, so I'm going to factor that out and leave what's left inside. So rewriting the left-hand side, that's x over x squared plus y squared to the 1/2 equals, again, I'm going to factor out the dy dx, and I'm left with the stuff inside. That's secant squared y minus y over x squared plus y squared to the 1/2. Okay, so now I have everything I need. I'm going to divide both sides by this right-hand factor, and I'm going to get my dy dx. So let me show you what I'm going to do. I'm going to divide this side by secant squared y minus y over x squared plus y squared to the 1/2. Okay. And so that goes on this side also. So that's going to be secant squared y plus y over x squared plus y squared to the 1/2. So I will get my final answer. It will not be pretty, but it will be my final answer. So I get dy dx equals the top. So this is going to be all over a big fraction bar. The top is going to be x over x squared plus y squared to the 1/2. And the bottom is going to be secant squared y. I put a plus here for some reason. This should be a minus. So this should be a minus. Minus y over x squared plus y squared to the 1/2. And again, it doesn't look pretty, but that would be the derivative of y, or dy dx, of this equation using implicit differentiation.